certainly if we're going to address things that are real threats right now, if there are real ones, because there are real threats. My whole issue is that the pretend threats obscure the real threat. Okay, let's get started. Next, speaking of hurricanes, Dennis, this is one of the things I brought tonight. This is fairly recent. This is, well, it's a year old, but it's still relevant. And I guess Al Gore has probably, and the global warming folks have not referenced this work here. This is a study, probably the most detailed study that's been done on hurricane activity over the last 5,000 years. And what they did was they went to a variety of environments that were near the ocean, where there were like these enclosed lagoons that were reasonably protected from normal sea storms, and that it would take a fairly large magnitude hurricane in order to bring in these, wind and sea. Like when the storm surge comes in, it leaves a layer of deposits. Okay, and then the hurricane's over and it goes back, and decades go by or whatever, and then another hurricane comes in. And so by going in and analyzing the deposits, they can see when the large hurricanes came through, and they used a variety of these kind of nearshore environments, they call them, to document along the east coast of the United States and then down on islands in the Caribbean when hurricanes had come in. Okay? And if there was a connection between hurricane activity and climate change. And what do you think they found?
Well,
No. Anybody want to speculate?
No.
Random.
There is. I'm going to...
The higher the temperature, the more the hurricanes. Because it's trying to move the heat from the center up to the north.
Okay, that's what you've been told. That's what we've all been told by Al Gore. On the basis of our age model, an interval of relatively frequent intense hurricane strikes is evident between 5,400 and 3,600 years before present, with the exception of a short-lived quiet interval between approximately 4,900 and 5,050 years before present. Following this relatively active period is an interval of relatively few extreme coastal flooding events, persisting from 3,600 until roughly 2,500 years before present. Evidence of another relatively active interval of intense hurricane strikes is evident between 2,500 and approximately 1,000 years before present. Well, then he goes on, okay. Evidence of hurricane landfalls in New York indicates periods of activity similar to those of the Caribbean islands over the past 2,500 years. In addition, sediment-derived records of intense hurricanes from the Gulf Coast also indicate a relatively quiet interval beginning about 1,000 to 1,100 years ago. Well, then he goes on to say when he looks at the sea surface temperature. So now what he does, and I'm going to take the graphs that he's got here and put them in, but I haven't done it yet. So what he does is he takes the graph of sea surface temperature and the graph of these episodes of these intense hurricanes, when they have these periods of intense hurricanes and when are the quiet periods. He overlays the two. And what he discovers is that it's during the warm times that the hurricanes are quiet, and during the cold times that the hurricanes are most intense. That's the essence of this. He kind of skirts around the issue somewhat in the way he talks about it. He says, like, for example, despite cooler Little Ice Age sea surface temperatures in the region, the sediment record indicates an increase in intense hurricane landfalls since about centered around 1700 AD. So there was the coldest part of the Little Ice Age, and that's so that the hurricane intensity peaked with the coldest part of the Little Ice Age.
Now, did he look at the disparity between the temperature at the equator and the temperature like north or south? I mean, because that might be what causes more...
Well, most of our hurricanes are... The hurricanes is pretty much confined to this latitude belt. There's an accumulation zone off the west coast of Africa, and across this
Right, yeah.
certain latitude, you know, it doesn't vary beyond that latitude. And a lot of it has to do with the configuration of ocean and land in the northern hemisphere. You have typhoons and cyclones like in the South Pacific, but they're more diffuse. I think hurricanes, you know, there's a certain, they can occur under, I'm not an expert on hurricanes, but there's a lot of different variables, and all of those variables sort of come together right in that stretch where we see them forming. Historical records from Puerto Rico also suggest an increase in severe hurricane damage in the 18th and 19th century. At least 16 severe hurricanes affected Puerto Rico between 1700 and 1850. And of course, 1850 is generally what's taken as the period at which the Little Ice Age began to finally sort of let go and things started warming back. And, you know, if you look at the trend of temperature, the transition into and out of these periodic coolings and warmings, it's not overnight, it's from a century to 2 centuries. So you actually now, I think the most accurate model is that there was a preliminary cooling between 1300 and around 1450 to 1500. Then there was a spell of warming, and then around late 1600s, early 1700s, it cooled again and reached its coldest, like at 1800 and 1850, and then started warming again. But then, within that warming, there's been coolings and warmings. In fact, it warmed, the first 3 decades of the 20th century was warming and culminated in the formation of the Dust Bowl, which was the combined effects of the heat and the drought and the bad farming practices, because the government was paying farmers to grow more crops than they needed. So because as soon as the government started giving the subsidies, then the farmers started plowing up all the land. That's a long story, I won't get off on that. In addition, an analysis of Caribbean hurricanes documented in Spanish archives indicates that 1766 through 1780 was one of the most active intervals in the period between 1500 and 1800 AD, when tree ring-based reconstructions indicate a cooler phase of the Atlantic multi-decadal oscillation. Furthermore, the sediment record indicates that an interval of relatively frequent intense hurricane strikes persisted over a millennium from 2,500 to 1,000 years ago, despite cooler than modern temperatures. So basically, the upshot of all this is that, you know, this guy looked and compared hurricane intensity to changing climate temperature and sea surface temperature, and discovered that it seems the colder it got, the more hurricane activity there was. And that last thing I read shows that what is generally considered the coldest part of the Little Ice Age coincided exactly with the most intense period of hurricane activity between 1500 and 1800 years ago. So again, do you remember Al talking about that?
No.
I don't think he did. Okay, then another item of interesting.
I've heard that before, that's like tracking.
Okay, so here's his final wrap-up, what he says in his conclusion. Given the increase of intense hurricane landfalls during the latter half of the Little Ice Age, tropical sea surface temperatures as warm or warmer than at present are apparently not a requisite condition for increased intense hurricane activity. In addition, the Caribbean experienced a relatively active interval of intense hurricanes for more than a millennium, when local sea surface temperatures were on average cooler than modern. So,
Does that mean there are tons of hurricanes during the Ice Age?
perhaps that could be. However, I've never seen a study done on that.
Maybe that's how all those mastodons got blown around over there in Siberia.
Well, maybe. Okay, catastrophic flooding origin of shelf valley systems in the English Channel. I had meant to actually make a graphic and put a map in here of England and the English Channel, but it turns out now that here is the English Channel. Let's get these. We're looking north through what's called the Dover Strait, and just up here out of the scene was what was called the Fennoscandian ice sheet. The Fennoscandian ice sheet was the big ice cap that covered Scotland, northern England, crossed because there was no English Channel. At the time, the British Isles weren't isles; they were connected to the European mainland, and the ice cap went across there and it covered all of Scandinavia. The big fjords that are in Norway, that are very similar to the fjords in west coast of British Columbia, were formed in precisely the same way by glacial scouring. But the southern margin of the glacier came right up here. And this is the English Channel, and basically it's a giant scabland channel. And there's been a group of geophysicists and geologists that have been studying it and have concluded that it is the consequence of a giant flood on the scale of the scablands, the Missoula flood. Not as big as the Missoula flood, but a gigantic flood, which they attribute to the failure of a chalk bench that held in a pro-glacial lake. So they're trying to invoke usually the same type of mechanism that seems to be the standard operating procedure for all geologists studying megafloods, is that you've got this big lake held in by some kind of a dam, and the dam gives way. Missoula flood, it was the ice dam. The Bonneville flood, it was a sedimentary plug in the Red Rock Valley of southern Idaho that gave way, and now here they're saying that there was a chalk bench, and I just haven't studied the whole article thoroughly yet. I believe they're saying that the chalk bench, no, that's just where the section is. The chalk bench must have been up here. Actually, maybe it's in this next graphic.
There's one thing that says bench on there.
Oh, well, maybe that was it.
Left of
Let's
the
see.
dashed line there.
Let's see, bench, paleo. Okay, I think it would have been up here. So here the ice would have been up here. And
Where was England?
This would have been England, and this would have been France, the mainland. And this is actually what we're looking here is like a view of the English Channel if you took the water out of it. And what the English Channel is, the English Channel, basically what is catastrophic flood origin.
That looks like it.
That's what they're saying. Well, right there you can see the Isle of Wight.
Yeah.
I don't know if you know your geography of the British Isles, but
So in the previous interglacial, was there no separation between France and England?
well, that's the question.
I'd say no.
That is the question. Right there is the question.
Well, it looks just like the one that had the big stone in the middle.
Yeah, Steamboat Rock.
Yeah, it's
Yeah.
exactly. That's what it was.
Well, if you drained away the water, those would be like Steamboat Rocks in the center there.
So there was an asteroid that hit up north from there and just flooded everything.
Well, I mean, something caused. I mean, this is clear evidence, and in addition to other evidence, that this Fennoscandian ice sheet also underwent catastrophic melting. So whatever the event was that caused catastrophic melting of the North American ice sheets, the question is, was it the same thing? Was it at the same time? I think it probably was, because we're seeing melting here on such an extraordinary scale that that whatever provoked it had to be something unusual. And something unusual, is it likely that that's going to happen? How often could we expect something like that to happen? I don't know. It's a 400, the English Channel, early marine geophysical investigations of the English Channel revealed a approximately 400-kilometer long network of submerged and partially infilled valleys carved into the bedrock floor. The network extends westwards from the Strait of Dover, collecting the drainages of southern England and northern France, before eventually amalgamating to form a single prominent valley. So anyways, this new work by this group here with Woods Hole, let's see, no, they're a Department of Earth Science and Engineering, Imperial College of London, UK Hydrographic Office. So mega flood events involving sudden discharges of exceptionally large volumes of water are rare, but can significantly affect landscape evolution, continental scale drainage patterns, and climate change. It has been proposed that a significant flood event eroded a network of large ancient valleys on the floor of the English Channel. This hypothesis has remained untested through lack of direct evidence, and alternative non-catastrophist ideas have been entertained for valley formation. Here, we analyze a new regional bathymetric map of the English Channel derived from high-resolution sonar data, which shows the morphology of the valley in unprecedented detail. We observe a large bedrock floored valley that contains a distinct assemblage of landforms, including streamlined islands and longitudinal erosional grooves, which are indicative of large-scale sub-aerial erosion by high magnitude water discharges. Our observations support the mega flood model, in which breaching of a rock dam at the Dover Strait instigated catastrophic drainage. We suggest that mega flooding provides an explanation for the permanent isolation of Britain from mainland Europe. So what he's saying there, what does he mean large-scale sub-aerial erosion? He means there the erosion is taking place not when it's under the ocean, but when it's, in other words, it's a flood over something that was on land, not under the sea. So you had a large-scale erosion, and that's what separated England from the European mainland.
Would that same thing happen then between England and Ireland?
Well, perhaps.
But see, if you take a look at the Isles of Man, the Isle of Man looks like a steamboat.
Does it? See, maybe. He says later in here, he makes a comment kind of ironically saying, we have more detail on the surface of Mars than they did until this study here with this sonar, collecting this high resolution sonar data. He says they had better resolution of landscapes of Mars than they did the floor of the English Channel. So now it had been proposed that the English Channel had been cut by catastrophic floods, but it hadn't been proven. And then he said, and one reason I don't know if you caught that or not, but because most of the time the geologists were entertaining ideas that were non-catastrophic. In other words, gradualist. But now he's saying with this evidence, it has all the earmarks of a catastrophic flood. And he goes on later in the article to compare the erosion here with the erosion that one would see in the Channel scablands, and compares it to the Missoula flood. So that's another little interesting detail that, perhaps more and more we're learning about the catastrophic history of the planet, and, beginning to recognize that there are these features and these details that, what do we think about the English Channel? Well, I think of, guys swimming the English Channel, so-and-so swam the English Channel, and if you know your history, you know that because of the fact that Britain is an island, that's why it became such a great naval power and sea power, and that was the basis for its, rise to dominance in the 17 and 1800s. But a lot of that is totally dependent upon the geography of Britain and its island geography. So now we learn that, it's almost certain now that the British Islands became islands because they were separated from the mainland by Now, what this would suggest to me is that was there a major event that caused a localization of meltwater to come off the Fennoscandian ice sheet right at this area, so it cut this big trough, and then with the rising of sea level, the trough then became submerged under the ocean, thereby causing England to become an island. All right, so here's the southwestern United States. Let me see how good geographers we are here. Anybody? I'll call out some features and let's see who can identify them. Death Valley.
The green on the left.
Where's Death Valley? Where's Death Valley? Who agrees with Elizabeth?
Maybe the yellow right above Baja.
Good. Where's Death Valley?
Pass the pointer around.
Oh, that's
All
good.
right, I should pass out pointers to everybody. Where's Death Valley? Anybody want to give it a shot?
Put a spot up there.
Who thinks they're a good geographer?
Put a spot up there, I'll tell you which way to move it.
Okay, let's see you, Charles. Okay, who agrees with Charles that that's Death Valley?
I
I
do.
vote higher in that, up more, over to the right,
Over to
That's
the
the
right.
San Joaquin Valley.
up like 4 inches. Whoop! It's either there or totally to your right. That big spot to your right.
That's salt flats. Oh yeah,
What is it?
that's salt flats.
That's the Bonneville Salt Flats right there.
So then it's the other one. It's the
Okay,
to the left.
come down, goes up, stop. That's it right there.
That's the
That's
front.
Death Valley right there.
This, yeah, that's it. Oh, no, I'm sorry.
Green,
It's
there
this.
you go.
That's it right there.
God, it's little.
Green's your lowest
Salt
point,
and
so
Lake.
Yeah.
you know it's
Salt
going to
and
be the
Sea
darkest
is right
green.
on in there too.
What is?
The Great Salton Sea.
Okay, where's Grand Canyon?
Probably out like
Right there.
Somewhere there, yeah.
Lake Powell,
right
there you
here.
go.
That's it right there.
Alright.
Grand Canyon. Where's the Mogollon Rim? Nobody knows that, do they?
sounds like a medical situation.
The Mogollon Rim. Sedona? Where's Sedona?
Oh, we like it there.
Anybody know? Can anybody see where Sedona would be on here?
I've been there before, but I haven't seen it.
Okay, Paul, you've been there.
I haven't seen it from this viewpoint.
It's right here. This is the Mogollon Rim. See, this is where, check this out. This is the Colorado Plateau right here. This is the Basin and Range province here. And this is the Mogollon Rim is the transition off the Colorado Plateau to, what's this? I don't know what this is called down here. What physiographic region?
Mexico.
Well, I know it's not. Well, actually, a lot of this is
Tortilla
Arizona.
Flats.
So this is the Mogollon Rim. How about Rio? Where's the Rio Grande?
Could be right on the edge of that fault.
Here's the Rio Grande, right here. The Rio Grande.
So that's right
Where-
down the middle of New Mexico.
Where's Great Salt Lake? Okay, good. Charles finally got one right. Okay. Where's Lake Tahoe?
To the left.
Oh, yeah.
That's Pyramid Lake. There's Lake Tahoe. Okay. Where is the San Juan Basin? Which is going to be where we're going to be looking at here. Within all of this
San Juan
area,
River.
where is the San Juan Basin?
Someplace like that.
That's it. Okay, very good, Charles. It's this right here. This kind of somewhat circular thing here, right here. This is the San Juan Basin. The San Juan Basin was pretty much, that was where the Chaco culture was concentrated, in that area and in the surrounding rim, in the rim country around. This is the Cheska Mountains here, which is really a beautiful little mountain range.
What's causing that that look right there?
Well, you have two things. Starting around 10 to 12 million years ago, you had pressures because of this. All these plates are moving this way. So, what you say is the Atlantic coast is a trailing continental edge, and this out here is a leading continental edge. And the theory of plate tectonics suggests that basically, like you see this basin and range,
Yeah.
that's a compression, it's a folding. So you've got the crust, and then you've got this folding. It folds, you have fold up, fold down, just like an accordion. And then, of course, the troughs are filled with sediment, and that's what gives them the flat floors. This whole area was like a big bubble that just bulged up. And once it bulged up, you see, now you got to bear in mind that on the rim of this plateau are limestones. These limestones, the youngest limestones, are like 10 and 12 million years old. So that's how we know that the Colorado Plateau's uplift has to be less than 10 million years, because limestones form in shallow oceans. So when that uppermost layer of limestone was forming, this was down below sea level. Okay? So now it starts bulging up, and only when it bulges up and becomes above sea level, and the higher it goes up to 5,000, 6,000, 7,000 feet above sea level, only then does the erosion start. So all of this erosion and the cutting of all of these canyons and stuff that you see here, like the Grand Canyon, is younger than the uplift of the plateau. You understand what I'm saying? The canyon couldn't be cut. You couldn't begin cutting the canyon down when all of this rock is down at the bottom of a shallow sea.
Right, yeah.
So it has to lift up. Now, if you go to the Grand Canyon and stand on its rim, you're standing on late Paleozoic rocks. So you're standing on rocks that are about 250 million years old. If you go north from here up into this area, this part of the country right here, you can kind of look right here and you can see there's another layer of rocks that's been eroded back. This is called the staircase right in here. And if you go stand up there, like by Zion Canyon, you now have rocks that are Mesozoic in age, the age of the reptiles and the dinosaurs, and they're over a mile thick. So those rocks at one time extended down over the rocks that you're standing on when you're at the rim of Grand Canyon. Now, so in other words, you're standing on the rim of Grand Canyon and you're looking down you're at 250 million year old rocks, and you're looking down at rocks in the bottom of the gorge that are 500 million years old and older. Okay, but where you're standing on the rim, that was once a mile to a mile and a half under more rock. And so when this was down below sea level, you would have had to have gone below sea level, then drilled a hole through at least a mile of rock, of Mesozoic rock, to get to the rock that's now at the rim of Grand Canyon. So what this is saying is, you don't start the cutting of the canyon and the stripping away of the layers of the rock until the plateau is lifted up above sea level. But you don't start cutting the Grand Canyon itself until you've removed over a mile of other sedimentary rocks that once covered the whole site. So what I'm saying here is that if you go to Grand Canyon and you're standing on the Grand Canyon looking a mile down, originally there was another mile of rock that would have been over your head, and it's completely gone.
Where did it go?
Where did it go? Tell me, where did it go? Well,
It has to be down in here.
it has to be the material that's composing all of this lowland down here.
And in 9 million years.
And in 9 million years or less.
And the reason that it goes from right to left is because there's more
From right to left.
Well, you say
From
the
east to west.
tectonic, it moves this way, you know? So is that because there's more volcanoes and
It's
new
because
Earth?
you've got one of the major spreading centers on Earth is along the Mid-Atlantic
What do you
Ridge.
mean by spreading section?
You have forgotten your lessons of Atlantis, where we talked about
That's
the
okay.
spreading of the plates at the Mid-Atlantic Ridge.
And that's where new land is made, essentially.
Yes, where
Okay.
new crust is made. Now,
And then they don't have that in the Pacific, those kind of things?
there is, yes. But what is
But it's
happening
not
here, the
as
whole
prominent.
North American continent is being pushed to the west.
So basically, the Atlantic new land making is stronger than the Pacific new land making, right?
Not necessarily. And that is why we have mountains. Because like for example, the Himalayas is when the Indian subcontinent moved up against the Asian continent, and nothing wanted to move. So what happens is the compression just starts buckling up the mountains. If you look at, let's see here.
Mount Everest has risen, what is it, 17 or 18 inches in the last 100 years?
They have found fossilized fish and sea stuff on top of those mountains.
Yeah. That's right. That's right. Exactly right. Okay, here we go. Here we go. Let's look at this one. Look at this feature. Now, to get oriented from what we were just looking at, there's the Great Salt Lake, okay, which is northern Utah. And here's the northern part of the Colorado Plateau, which stops basically here. And then it's just the Rocky Mountain Range from here. Look at this feature, what is called the Snake River Plain, that stretches across southern Idaho in this big arc shape, this big bowl shape here. Where's Yellowstone? Charles, you still got the pointer?
Yeah.
Where's Yellowstone?
I'm gonna guess. It'll be right in here somewhere.
Right here, there's Yellowstone Lake. Yellowstone is right here. Now, we've all heard stories about how Yellowstone is a volatile place, right? And that there's all kinds of thermal and seismic and volcanic potential activity in the area of Yellowstone. Now, this is a whole nother lesson that I want to get into at some point. But you now also know up here, this is the Columbia what plateau is it called? The area where the Missoula floods came across? Scablands. And what kind of rock is it in? Basalt. Remember basalt, which is what kind of rock? Hard, igneous, lava rock. It's basalt is rock that's extruded as very fluid lava.
Born in fire.
Now, yeah, okay. This whole thing here is what is called the Columbia Basalt Plateau. And in fact, the basalt actually goes through and creates part of the walls of the Columbia Gorge right there, and is actually all the way out to the ocean.
And show us where some cities would be on that coast. Like just
Okay, Portland would be right here.
Okay.
Seattle would be up here.
Okay.
This is Vancouver Island, so Vancouver, Canada is there. You know, this is Puget Sound right here. You got it?
Got it.
Right. Okay, so now check this out. Check this out. At Yellowstone, under Yellowstone, there's a big zone of intense thermal activity. It's still active, right? It's heat, a lot of heat down there
About 10 million more years.
before it finally wears itself out.
Before it moves across underneath that mountain range,
Oh, okay, well,
which is going to basically seal it off.
the oldest basalts that formed the Columbia Basalt Plateau are about 16 million years old. Now, around 16 million years ago, right in this area here, look carefully at that area, right there. That's a very interesting area. Something happened right here. All kinds of fissures opened in the earth, and this fluid basalt started flowing out, and it flowed to the west. Out of this region right here is the source. This whole irregular kind of semicircular region right here, or circular region. You can see it right there, right? See it right there?
It's a flower.
That is the source where all of these cracks and holes and fissures opened up, and all of this fluid lava poured out in pulse after pulse, wave after wave, thousands of feet thick, ultimately, thousands of feet thick.
Is that a caldera?
Well, it has not been identified as a caldera, but I'm suggesting that it once was. Now, two of the leading geologists that have studied the Missoula flood, David Alt, and I forget the other guy's name, actually proposed a very interesting idea. There is what is known as the hot spot right here. Okay, now, if we take the conveyor belt of North America and we back it up 16 million years, this is what happens. This spot right here, where the wound was, if you want to say it, the wound from which all of this fluid basalt pulsed out, flowed out, almost like blood out of a wound, over the last 16 million years, this right here was not here. It was here. Did you get that? 16 million years ago, it was almost as if somebody turned a blowtorch on the bottom of the lithosphere right here and begin melting the surface rock that all begin pouring out. But you've got a picture. It's like this. Here's the hot spot. The plate is on top of it. The hot spot is causing all of the melting and the outflowing of basalt. but the plate on top is not fixed, it's moving. It's moving across, so as it moves, and it's not moving in a straight line, it's moving in a big arc. So as it moves over this hot spot, the hot spot creates this zone, this melted zone, and that's what you're seeing traced right here. So 16 million years ago, this jumbled circular area was right over the Yellowstone hotspot. The plate moved to the west, it shifted to the southwest, then it got pushed and started going back to the northwest, and it's moved this far into 16 million years.
And what's in that little view? What are there farms or cities or what's in that?
This is the Snake River Plain.
So it's a park or a
Park, yeah. It's a large, vast area. Vast area. I can show you pictures
okay.
of what it would look like.
No,
It's a very cool area. The Snake River flows through here.
Well, this was 80 miles by 400 miles or something
Yeah,
like
it's
that.
probably 80 miles wide, 400. Craters of the Moon is right up here. And Craters of the Moon was one of the most recent big outpourings of lava in this area, and it happened right at the end of the last ice age, 10, 11, 12,000 years ago.
And is that why?
And undoubtedly, as a result of crustal stresses set up from the transference of all the weight of the glaciers melting.
Now, is that why all the volcanoes up in that area are still kind of, not active, but kind of active?
Well,
More
those
active
those volcanoes are all in this rim right here.
well, that's pretty
And
cool.
that is because the North American plate right here is riding over the Pacific plate. So here's what's happening. Here's the North American plate like this, coming to the west. Here's the Pacific plate. The North American plate is being pushed up over the Pacific plate, which is going down under and piling up and creating tremendous seismic and volcanic pressures. And that rim where that zone where that pressure is the greatest is right here under these mountains where the volcanoes are.
And is that kind of what's going on with the San Andreas and all the way down California? But
Kind
there's-
of, yes,
but there's
except
no
that the San
volcanoes.
Andreas is actually, it's moving this way. It's shearing in a north-south direction.
So it's not overlaying.
Right. There are different kinds of fault systems. And so what you have here is called a subduction zone. The Pacific plate is being subducted under the North American plate. And what it does is it pulls all of this stuff down, and as it plunges down into the crust, all of that crustal rock begins to melt. And it's probably also carrying water and all kinds of stuff, and it begins to melt, and then it begins to force its way. And now new rock is being pushed against it, so it's melting and it has no place to go except to push up towards the surface. And that's where you get these, like here and there. You've got Mount Adams, Mount Hood, Glacier Peak, Mount St. Helens, Mount Shasta, Mount Rainier. All of those are volcanoes because of that.
Baker.
What? Baker? Yeah.
And which one is the most likely to pop, would you say?
Oh, I don't know. Which one's next? Probably, let's see, has Mount Baker been showing some activity? Is that the one? Yeah, Mount Baker could be the
More
next.
so than
Mount Hood.
Yellowstone. They're doing a lot of shows on how Yellowstone is just gonna like.
Well, it could. I mean, it could someday. I don't know if it's necessarily something we have to
Yeah.
be concerned about in the next decade or two or even century. But now what David Alt proposed, and this is to me is a very interesting idea. He suggested that around 16 million years ago, there was a hole punched into crust. Right here. Of course, this area here, 16 million years ago, was back here. You got a picture. Okay, and what he suggested it would be a small, very dense, fast-moving metallic asteroid that comes in more or less perpendicular to the surface of the Earth, and probably a head-on collision. Because now you know if the Earth is moving through space at 18.5 miles per second, which is 66,600 miles per hour, and it meets an object that's also going that fast but in the opposite direction, you've got a head-on collision. If Earth gets pummeled by something coming from behind it, it doesn't have nearly the kinetic energy of impact as a head-on collision. What David Alt proposed was that perhaps there was a head-on collision between Earth and a small, dense asteroid, which, run the physics on it, is capable of punching a very deep hole right through the crust into the mantle. And he proposed that as the origin of this hot spot. In fact, I'm of the mind that this could turn out to be maybe the most likely explanation for most of the localized global hotspots. Maybe indications of where, it'd be like the difference between if somebody shoots you at point blank range straight on, or you get shot and you get a grazing wound off the side of you. This is one where, like, you know, and then of course the cosmic animals that the Earth could encounter, there's a variety of those, you know, from low density comets to middle density stony asteroids to high density heavy iron asteroids. So if you had a small, like 1 or 2 mile in diameter iron asteroid meeting the Earth in a head-on collision, it could puncture a hole 30 or 40 miles deep into the crust and then spend the next 10 or 20 million years healing. And that could very well be what happened right here. And then what you'd be looking at here is this would have been the scar of the impact right here. And of course, there you don't have the preservation of a crater because the object has punched through the crust, and now you have this upwelling of all of the basalt, which is going to obscure the crater, which, you know, so you don't see a big bowl-shaped crater or even a multi-ring crater like you normally would. Instead, you get an area of jumbled, broken, fissured rock that has all of these deep-seated magmas coming up and pouring out through it. Exactly what you have here. And you'll notice this is kind of, it fits because you look at the scars when, you know, almost circular. But there's no proof yet. That's just purely hypothetical. But it makes sense.